Here I will show you how to use Bayesian ANOVA or Bayesian A/B testing in R using the very famous STAN library for Bayesian analysis. You can download Python from its website over here for Windows. You can also download my project from the following GitHub link. In a previous video I showed you how to load this website example dataset which contains our data for our A/B testing. In this dataset we had a website flag which was standard, blue or red, so three different experiments or two different experiments run on a standard website where the background was changed. Then we have a blocking variable, also an external factor that we are not interested in but we think might be contributing to the variability in the data, which is whether there was a coupon discount or just standard for each observation. So coupon discount should in theory increase the amount of the purchase size that people do on this website, and total is how much money people spend on average on that website for that particular hour. So what we did there was to load the data, then we did some plots, then we did the ANOVA model, and then we analyzed the residuals, and finally we did the comparisons between the different experiments, so standard, red, and blue. You can check that video here below. At the end you can see that blue, red, and standard, they are different, but whether they should be considered different is a different story because that depends on the variability, and that's why we need a proper statistical test as we did here. In this example I will be doing something slightly more convoluted, which is to run this through a Bayesian model. Here I will be loading the data in the same way I did before, but here I will be generating a new data frame. So this is my initial data frame. I added a few things here that you can see in these if-else statements. What I want to do here is to create a set of dummy variables, so variables that take 0 or 1. For the experiment it's standard, red or blue. So I wanted this to be 1 for the cases where the observations correspond to a standard website, 1 for blue as you can see here, and then the ones for red. So always there is one that it's going to be 1 and the other two are all going to be 0. And for the coupon I want this to be literally 0 or 1 because the coupon has two possible values, yes or no basically, so it will be a 1 or a 0. So I want to create this numeric data frame, everything is numeric, because I will be feeding this into STAN. So in order to use STAN you need to install this RSTAN package. It takes some time because it's very big, but it's incredibly powerful. So whenever you load this you'll get some warnings and some messages about how this was built, but this is probably not important. And in my case I will be, as I said before, using this data frame. Bear in mind that I'm also creating this one here. This is not a data frame, this is just a list or a vector that contains the variable that I want to model, this total thing that is here. So then comes the model. Looks scary, but it's actually not that complicated. So my model is the following. I have a vector y that will be distributed according to a normal distribution, so it's standard Gaussian. X is my matrix of values that I have here, so this is my x. Beta is a vector containing the coefficients, even though the word coefficient in the Bayesian context is not great, but anyway. Sigma will be the variability. And then I need to specify priors. What are the priors? So the priors are our prior expectation, our prior idea about how we think these beta variables are. So what I'm doing here is putting very loose priors because I'm not sure. Maybe a prior can be obtained by talking to people or just by previous analysis. It is never determined by looking at the data. It needs to be done prior to looking at the data. So that's why it's called prior. In this case I am putting very loose priors, so these are just normal distributions. So this means that I don't know the effect of each one of the experiments or the standard one. I think they should be centered around 100, but I have no idea. And I am putting a quite loose Distribution here, this controls the sigma, the variability, and I'm just going for 40. I have no idea what should I be using. If you had any different ideas, so for example, it could be the case that you think that the red color, the blue, or the blue color examples, they just be providing you on average an uplift of 50 over the standard one. So maybe you should be doing that. That's one possibility. The final thing that I want is to specify a prior for my beta. So my beta 4. My beta 4 in my example will correspond to the coupon one. So the coupon is 1 or 0. Again, I'm not sure what's the impact of the coupon, so I'm just putting 0 because I don't know. And I'm putting a quite big standard deviation. And we'll see where this ends. The other thing that we need here is to specify which are the parameters that we have. So we have a beta vector, which will contain k elements. In my case, k is equal to 4. And then we need to specify the sigma. And we can put here the lower boundary. So obviously it needs to have a lower bound on 0. So we can specify the lower there. This happens for any linear regression example. The sigma should be constrained to lower 0. And then we need to specify the data we'll receive. So this is very simple. N, k, x, and y. These are the dimensions, so my X matrix will contain n elements and 4, k is equal to 4 columns. The reason we also need this is because obviously this should be positive. And then we define a list. List, we specify how many elements do we have? Well, the n row of X. How many columns? We have 4. What is the modeling data? X. What is Y? Y. And then we code feed our stan, and we pass our model, and we pass the stan data. It's actually simple, right? So what is the objective of this? The objective of the Bayesian approach is that we don't treat the coefficients as fixed numbers that we want to compare as we did here in the previous example. The objective here is to think that we have distributions for those coefficients. Each one of these coefficients is associated to my experiment, but they're not coefficients, they're distributions, they are random variables, they just move, they take any value that they want according to the support of that distribution, but we're not worried about that here. And in my case I am just saying, well, I don't know the value, it could be between -infinity and infinity, and it should behave similar to a normal. And then the objective is to use the data to update these priors to end up with the posterior distributions. So this means that we'll grab the priors, enhance them with data, and then we'll come up with a new idea on how they look like. The objective is to create this final distribution for each one of them. These are called posterior densities. And we actually want to draw them, plot them, use them, and that's what we will be doing. So we call feed our stan. You can see what I'm doing here. We are printing the values. This is usually not very important because it's hard to see. And then this is the important bit. These are the results. You can see that the mean for each one of them are these ones, the standard deviation mean, the SD mean, and then we have the percentiles. Maybe this is not very easy to see, so what we usually do is to plot them using some tool and see how they look like. So before looking at that plot, I want to draw your attention towards the trace plot. So in the trace plot we see the chains. Understanding if a chain converged to the point where it gives us reliable results is something quite complicated. It's kind of an art. But long story short, what we want here is to make sure that these trace plots here look exactly like this. You see they don't show any kind of structure, they just go up and down randomly, and that's exactly great. But if they, for example, went up, and then down, and then up, then that's where we would get worried, and that's probably not great. But everything here looks good to me. They're different colors because they're different chains. So essentially what happens is that this gets sent into each core in your computer and everything then gets combined. And where does it get combined? It gets combined, for example, in this function. So the MCMC intervals. This function is not from the rstan package, it's from the base plot. So you need to install it as well. And this is exactly what I wanted. So this is the posterior mean. because I indicated I wanted the posterior. There you have it. And then there is some confidence interval. We shouldn't be talking about confidence interval in the Bayesian world because the concept is different from the classical statistical term, so that's probably not correct. Anyway, the idea is to plot what's the likely area where we would expect the mean to be located, if you want. So what we can easily see here is that beta 2, which in my case beta 2 is the red one. So the red one doesn't provide much of an uplift. You can see that, yeah, it's somewhat better, but the confidence interval, so I'm plotting two of them, 0.80 and 0.99. So the 0.99 is the wider one, by the way. They kind of include potentially the standard case. So I'm not very sure this provides an uplift. Maybe it does, maybe it doesn't. But for sure, the third one here does provide a great uplift. You can see the difference here. This doesn't include this. If we projected this upwards, this wouldn't include any of this. And finally, one thing we usually do is that we plot the posterior densities. So remember that I was using Gaussian ones here as priors, and this got updated, right? So now the means you can see, the means are not 100 anymore, of course, 100, 106, and 129. So this changed. So the data was used to augment them. And you can exactly see the same thing here. Even though the beta 1 mean is around 100, beta 2 is probably around 100, 108, 107, the mean. For beta 3, obviously, the mean is closer to 125. So why is the Bayesian approach used sometimes in A/B testing? Mainly for one reason. One problem with the classical approach in A/B testing or in ANOVA is that we usually need to specify a defined threshold for our test that we use here in the multiple comparisons between the treatments, or here in the proper ANOVA. We usually define some statistical criterion, we define a p-value, and then we do the comparisons, and that's fine. The problem is that when we have a website, for example, and we're running an experiment, we do it on Monday, and then we probably would like to look at it and see how it goes. And then we look at Tuesday, and we look at Wednesday, and look at Thursday. So every day that we do, we're actually doing kind of a sequential test where we're looking again, looking again, and looking again, and looking again. That kind of breaks the concept of statistical significance. The p-values that we think here are, for example, 0.05. In that case, when we have a recurrent approach and we look every single day, that really changes things, and the p-values there are no valid anymore. So what people usually do in the A/B testing world is that they define a very specific time frame. They say, well, we won't be looking at this for 7 days, and we will only look at the results next week, right? Which is good, but it doesn't give you that kind of real-time update on what's going on, right? You can't be constantly looking at them. Why? Let me put you another example why this. Imagine we looked at the results every minute. So if we look at the results every minute, it's likely that just by random chance we'll be, for example, rejecting a lot our tests here. Well, just because we're looking at it many times. The Bayesian approach is fine with that. It doesn't care. So in the Bayesian approach, we can be actually looking at how the posterior densities get updated every single minute, and that would be fine. And we can see if these three distributions are always kind of the same, or if they start to diverge and start to change. So if we have this thing here, and then the beta 2 or beta 3 start to go to the right, taking more and more values, then that's absolutely fine. We don't have any kind of statistical problem with that.